Right. So we are happy to have Daniel Bragg of Berkeley. He'll speak on compact supersingular twistor spaces. Take it away.
Great, thanks, Shandor. So I wanted to start by, everything I'm going to say today is it's about a bunch of constructions related to certain K3 surfaces. I think large parts of what I'm going to say I expect or know apply to maybe more general classes of varieties, but everything kind of specific I'm going to say today is just going to be restrict myself to K3 surfaces. So I'm just going to say a few words about K3 surfaces, what a supersingular K3 surface means, and then I'll start talking about the constructions and the twistor spaces and so on. So here's just a few words about K3 surfaces to get us going. Okay, so I'm going to work over an algebraically closed field. Here's the definition of a K3 surface. It's a surface with trivial canonical and H1 of O being 0. Here's a consequence of this definition. This is the Hodge diamond of a K3 surface. This is all I'm actually particularly interested in the case of positive characteristic, and I guess the computation of these Hodge numbers is kind of non-trivial in positive characteristic, but it's still true. They're still they have these same values as they do over the complex numbers. Here's the Betty numbers of a K3 surface. These specific numbers will come up in a second. The central Hodge number is 20, and the middle Betty number is 22. Okay, so what is a supersingular K3 surface? There's a bunch of different characterizations, but here's one. Let's say X is a K3 surface. The Bragg group of X is a free Z module of some finite rank row of X. This is called the Bragg number of X. And you can bound the Bragg number in terms of some cohomological invariance. So if the characteristic is 0, then the Bragg number is less than or equal to this H11, which is 20, like I said in the last slide. So the biggest it can be is 20 in particular. I think K3 surfaces with Bragg number 20 are sometimes called singular. I think singular being in the sense of like particularly interesting or something, not in the sense of non-smooth. So that these are all smooth. Okay, but if the characteristic is positive, you only get a weaker bound. The weaker bound you get is that the Bragg rank is less than or equal to the second Betty number, which is 22. And the Bragg rank really can be strictly bigger than 20, so it can be as big as 22. And this is one way of defining a supersingular K3 surface. So it's supersingular if it's a K3 surface whose Bragg rank is 22. So I think my understanding of the terminology is that it's supersingular in the sense that it's sort of like even more, I don't know, even more interesting or even more sort of symmetric than it's possible to be in characteristic 0. Okay, so this is like I think probably maybe the most like elementary, the most quick way to define a supersingular K3 surface. So what's not obvious from this definition is, first of all, like even if these things even exist, so they do. And here's two sort of quick examples you can write down. One example is to take E to be a supersingular elliptic curve. The word supersingular there having its own definition. And you can take E cross E and then take the Kummer surface associated to that abelian surface. And that is a supersingular K3 surface. So that gives you one in every positive characteristic. Here's another example. You could take the Fermat quartic inside of P3, given by that equation. And if P is 3 mod 4, this is a supersingular K3 surface. If for the other P's, it's a K3 surface. It's supersingular when P satisfies that condition. Okay, so those are two. I mean, and I guess the second one at least is not saying that that's definitely not easy to see at all. But you can compute the Picard group of this. I think that was done by Shiota first. Okay. So that's a supersingular K3 surface. I think what's definitely not obvious in this definition is that these things have some kind of really interesting behaviors, and at least in some sense, I think if you're looking for kind of interesting phenomenon over the in positive characteristic, supersingular K3 surfaces or varieties exhibit a lot of sort of interesting new things. So here's some facts about supersingular K3 surfaces that I think some of these might be kind of surprising if you haven't seen this before. So let's say K is algebraically closed with characteristic P. There's actually a lot of supersingular K3 surfaces. There's a 9-dimensional family of them. If you're sort of used to the theory over the complex numbers, as the Picard rank of the K3 surfaces gets bigger, the deformation space gets smaller. So like when you get to singular K3 surfaces with Picard rank 20, they have discrete moduli. And so but somehow when the Picard rank is 22, that's not true at all. Now there's all of a sudden big families of these things. And something that's also interesting is there's even families of supersingular K3 surfaces over complete bases, non-isotrivial families over proper schemes, proper varieties. In fact, the universal family, there's universal families that are 9-dimensional and complete. The base is complete. Okay, so here's kind of my well, I wanted to give you an example of a very concrete construction of a family of supersingular K3 surfaces over a complete base. The complete base is going to be P1 in this case. So I think this is a really cool construction. If you haven't seen it before, hopefully this could be like a takeaway from this talk. So this is, I'm going to call it the Moret-Bailly construction, or the Moret-Bailly family. So here's how it goes. We're going to start with the supersingular elliptic curve, E. And here you could take this as a definition of supersingular or a consequence. E being supersingular means that there's you can find the group scheme alpha P sitting inside of E. So here alpha P is the kernel of the Frobenius on the additive group, or specifically it's spec of K join X mod X to the P. With group law given by addition. Okay. Now I want to look at E cross E, and one thing you can show is that there's a bunch of copies of alpha P in E cross E, and they're specified by giving lines in the tangent space to the origin of E cross E. So given at least one direction of this, I think you should be able to see immediately. If you're given a copy of alpha P sitting inside of E cross E, then as a closed subscheme and a closed subgroup, alpha P has a 1-dimensional tangent space. So you get a tangent vector in the tangent space of E cross E at the origin. And actually this is a bijective correspondence. So the tangent space of E cross E at the origin, that's a 2-dimensional K vector space. So this tells you that there's a whole family of embeddings of alpha P in E cross E parameterized by the space of lines in the tangent space of E cross E, the space of lines in this vector space. Or maybe it's dual, depending on your conventions. So there's a whole family of embeddings of alpha P in this E cross E. And now this is you can use these to make families of varieties. So here's I have an extra floating Moret-Bailly family. First, let me describe the family of abelian surfaces. This is going to be I call it curly A. What you do is you take E cross E cross P1, and at each point you mod out by a different one of these alpha P's. And this gives you a family of abelian surfaces over P1. They are supersingular in an appropriate sense of that word. Okay, so and given this family of abelian surfaces, you can now make a family of K3 surfaces by just taking the associated Kummer surface above each point. Okay, so this construction, this is a construction of a smooth family of supersingular K3 surfaces over P1, in kind of this really pretty direct and kind of beautiful geometric way. Great. So this is one family of supersingular K3 surfaces over a complete face. And one of my goals of what I'm going to talk to you, or I could take this as like one of my motivations for doing this, is to try to find direct sort of geometric constructions of other families of supersingular K3 surfaces over complete bases, like for instance over P1. The previous construction, the Morey-Bailly family, it's very specific to that geometric situation. So that gives you sort of, I mean, I guess the way I put it, for each supersingular elliptic curve E, this spits out a family. It actually turns out it doesn't matter what supersingular elliptic curve you started with. So that really only outputs one family of supersingular K3 surfaces over P1. We know that there are tons of them from the general theory. So there's a 9-dimensional complete moduli space of supersingular K3s, and there's tons and tons of P1s in there. And so one of my goals is to find kind of direct constructions that apply in a more general setting than the Morey-Bailly family. I mean, I'll come back to this in a second, but I guess one of my motivations for this is if you had a sufficiently strong mechanism for doing this, this would let you, for instance, like give another proof of the Tate conjecture for supersingular K3 surfaces. The Tate conjecture for supersingular K3s is now known by work of many people, and there's several different proofs. But I think you had some kind of mechanism for doing this. This could let you do let you find another proof, and I think that one that would, for instance, avoid using like the Kuka-Satake construction. So that was one of my motivations for investigating this. All right, so I want to, so the compact twister spaces that were in my title that's my name for these things. This is building off a construction that I worked out with Max Lieblich, which we called supersingular twister spaces without the word compact. So I want to spend a few minutes kind of saying what the main idea behind that construction was, because what I'm kind of the new work I'm talking about today is extending that construction by compactifying it essentially. Okay, so here's kind of our supersingular twister space story that we worked out a few years ago. Okay, so let me let X be a K3 surface, not necessarily supersingular for the moment. And I'm going to consider the following functor. I'm going to take H2 of X mu n, but now with an underline to be it's the sheavification of this functor here. So this is like this kind of looks a lot like, for instance, the Picard scheme, the Picard variety. There's just there's a 2 instead of a 1 in the superscript, and I'm looking at cohomology with coefficients in mu n instead of gm. Okay, so here's a theorem that you can show. This functor is actually representable, and this term is actually not. It's not at all. It's not like easy to prove this. At least I didn't find it easy. Artin claimed this in his Artin wrote a paper on supersingular K3 surfaces, and claimed this result and said the proof would appear elsewhere. But I don't think it did, as far as I can tell. Max and I wrote down a different proof, and in some other work that I have with Martin Olson, we kind of generalized this theorem to some more general class of varieties. But in any case, it's representable. So it's some finite type group scheme over K. Okay, and so it's a group scheme over K. So you could take its connected component of the identity, and you could ask what it is, and you can actually relate this connected component to other cohomological invariants of X. And one output of this is that X is supersingular if and only if this connected component is isomorphic to A1 as a variety, or as a group scheme, it's isomorphic to GA. And I guess if X is not supersingular, this U that you get is always discrete. It's zero dimensional. Okay, but in supersingular case, the fact that this group scheme is positive dimensional means you can do something kind of interesting. You can one consequence of this representability is that there's a universal class, which is a class in H2 of X cross A1, comma mu P. Oh, sorry, I should have said this explicitly. I started out with looking at mu N, and then I switched to mu P just after the theorem.
Also, sorry, do you switch to the representing object from the functor, or?
Yeah, let me, I guess when,
so when you say connected component, do you mean the?
Oh yeah, yeah, absolutely, yeah. Yeah, absolutely, yeah. I'm conflating the representing object and the functor there. Yeah, definitely. Or maybe you could, yeah, maybe you could try to define it functorially or something. But yeah, yes, what I'm saying is take a representing object, take the connected component. Okay, so one consequence of this representability is that there's kind of an interesting class alpha in this cohomology group, or you could also look at its associated class in the Brauer group. So I call that alpha tilde here. That's a class in the Brauer group of X cross A1. And this class it's universal, meaning basically if you restrict it to X cross T for some T in A1, you get some class on X, and it's the class corresponding to that point in A1. And in particular, this alpha tilde is non-isotrivial, so it's not pulled back from a class on X. Okay, and the existence of such a thing is very special to the supersingular case. Okay, but once you have this class in hand, here's a construction that you can do. You can take a Mukai vector, so that's some sort of discrete invariant, and you can make a relative moduli space of alpha tilde twisted sheaves. So if you pick any Mukai vector, pick a polarization, which I guess I'm suppressing here, and then there's a general theory of moduli spaces of twisted sheaves on varieties, and particularly on K3 surfaces, and you can sort of plug this into the general theory, and it outputs some other family of varieties over A1. So the moduli space of semi-stable twisted sheaves. Okay, and there's also, in this specific setting, these moduli spaces are very nice. If you pick pick V appropriately and pick your polarization appropriately, then you can get out, for instance, a family of K3 surfaces. And in this case, the K3 surfaces are going to be supersingular. Okay, so this construction is what we call supersingular twister spaces. So just zooming out for a second, the construction it takes in, you start with the supersingular K3 surface X. There's this kind of universal cohomology class on it, this universal Brauer class. And then given any primitive Mukai vector, or any Mukai vector with satisfying certain properties, like it has to pair with itself to be zero under the Mukai pairing, and given a suitable, sufficiently generic polarization, this outputs a family of supersingular K3s over A1. And these families are in most of the time going to be non-isotrivial. So this is a genuinely interesting variation of supersingular K3 surfaces. You can think of it as kind of the universe in the universal setting. You have a supersingular twisted K3 surface, a twisted supersingular K3 over A1, where the underlying supersingular K3 is just X cross A1, so it's isotrivial. But the Brauer class is non-isotrivial. And then when you take this moduli space, if you take an appropriate V, now sort of the non-isotriviality gets transferred into variation in the moduli spaces. Okay. And in fact, as this construction recovers the Moiré by E family, or at least the Moiré by E family minus a point. This is only a family over A1. The Moiré by E family is a family over P1. Okay, so the goal, like a more specific version of my previous goal, is to find some kind of direct way of compactifying these supersingular twistor spaces. So but by this, I mean like one knows, from kind of the general theory of supersingular K3 surfaces, kind of general results, that there does exist a family over P1 extending this family over A1 that I just produced in the previous slide. In a special case of this being the more A by E family extending one of these. In fact, that essentially always happens, that there does exist a family, sort of a K3 at infinity filling this in, but the construction that I had on the previous slide only gives families over A1. So my goal is to extend this construction, find like a more general version or a variant that produces the family over all of P1 in some kind of sufficiently sort of direct way so that I can use it to, like I said, one goal is to use it to do things like say something about the take conjecture. I think also it's the construction ended up being pretty interesting in its own right. But. So what is the problem with doing this with the previous construction? Well, the problem is that this universal class alpha tilde does not extend to a Brauer class on X cross P1. So the construction, at least as stated, it does not work. It does not produce this full family. Okay, so what I want to spend the rest of the time talking about is my more recent work, finding a construction that does produce these full families over P1 directly. Okay, so here's one clue that I found kind of intriguing. You can actually compute kind of from the more of this general theory what the variety at infinity has to be, and it turns out it's the inverse Frobenius twist of the variety of the surface over 0. I found that kind of intriguing, but anyway. Okay, so I want to try to describe this sort of new construction, and I wanted to start by recalling Cartier descent, because that's kind of the starting point. So this is let me put myself in this setting. So let's say X is a smooth K scheme, and E is a coherent sheaf on X. And let's say we're given an integrable connection on E, nabla. In characteristic P, there's something called the P curvature, which is defined by this formula. So here, I think the key thing to notice is that D to the P, that's in the bottom right of this definition, D to the P is the P iterate of D, D being a derivation of the structure sheaf of X. And the special fact about being characteristic P is that the P iterate of a derivation is again a derivation. So it makes sense to take nabla, so D to the P. And it turns out if you take this difference here, this defines a linear map from the tangent bundle of X to end E. That's not at all obvious, but this map turns out to be linear. And that's this map is what's called the P curvature of nabla. Okay, so here's an example of how such a thing, a connection arises in characteristic P. If you take a coherent sheaf E and you form its Frobenius pullback, you pull it back by the Frobenius, there's a canonical integrable connection on this sheaf that happens to have P curvature 0. And the connection is defined by this formula that I wrote down there. You take S tensor F2, S tensor 1, tensor GF. So when you can check that this is a connection, that it's also integrable, and you can also check that its P curvature is 0. And Cartier descent is the statement that essentially every such connection arises in this way. Oh, and I guess I should say if you take the subsheaf of horizontal sections of this thing, you just get back E. And that's Cartier's theorem that Cartier proved. This defines an equivalence of categories. Coherent sheaves on X are equivalent to coherent sheaves on X with an integrable connection with P curvature 0. And the correspondence being take X and form its Frobenius pullback and equivalent with the canonical connection, and going the other direction, you take such a thing and you take its subsheaf of horizontal sections. By horizontal, I mean sections that go to 0 when you apply the connection. All right. So this is some kind of very classical thing. And I want to describe kind of a generalization of that. And the generalization is basically that there's a version of Cartier descent for twisted sheaves, certain twisted sheaves. So let me at least describe what the output of this is. So if you have a Brouwer class on a variety, and you pull it back by the Frobenius, it becomes P times the Brouwer class you had before. This is basically because Frobenius pullback on the group of the multiplicative group raises functions to the p power. Right, so what that means is if you have an alpha twisted sheaf on a variety, then the Frobenius pullback is a p alpha twisted sheaf. So in particular, if p alpha is 0, in other words, if alpha is p torsion in the Brouwer group, then the Frobenius pullback is an untwisted sheaf. It's a 0 twisted sheaf. So I think that is pretty suggestive that there should be some kind of generalization of Cartier's descent result that should give you some kind of equivalence between alpha twisted sheaves on X and something like sheaves on X with some kind of connection. Here, if under the assumption that alpha is a p torsion class in the Brouwer group. Okay, so it turns out this does work, and you can work this out. So I'll say a few words about it from kind of a few different perspectives to try to give an idea of what's going on here. I found it actually kind of really helpful to think about in terms of cocycles first. So here's a description of how you do this in terms of cocycles. So let's say you have a Brouwer class, and let's say you pick some cocycles representing alpha. So some alpha sub ijk's. So this is like a 2 cocycle. Once you pick this cocycle, you can describe alpha twisted sheaves as being tuples. You have a bunch of sheaves EIs on each of your open sets, and you have isomorphisms but on the overlaps that don't quite satisfy the cocycle condition. They satisfy this twisted cocycle condition that I wrote here. So that if it was a cocycle condition, you'd have this alpha ijk being replaced by 1. But this is only an alpha twisted sheaf, and so this is the condition you get. And so this is the usual description of an alpha twisted sheaf in terms of a cocycle. Okay, so let's see what happens if we pull this back by the Frobenius. Oh, that was a lot of stuff at once. Okay, so I want to pull back this data by the Frobenius. So each of my EIs becomes fx upper star EI. So that's what this Fi is. And each one of these has a connection on UI, the canonical connection. And this twisted cocycle condition becomes the size, this equation with the size equals alpha ijk to the p. Okay, so this is what happens if you take the usual description of an alpha twisted sheaf in terms of a bunch of sheaves satisfying this twisted cocycle condition, and you just apply Cartier descent to each. You apply Frobenius pullback on each open set, and just write down what the equations become. This is what you get. Okay, but now let's suppose that p alpha is equal to 0, and let's kind of massage this a little bit. That means that the cocycle alpha ijk to the p is equivalent to 0 as a cocycle. And what that means is that we can find a boundary, which is a bunch of beta ij's satisfying this condition, beta ik, the inverse, etc., equals alpha p, the alpha ijk. And if I set psi prime equal to what I set it equal to, then this tuple, the Fi's, actually satisfies the cocycle condition. I mean, this is sort of expanding on what I said before, that the Frobenius pullback of E should be a 0 twisted sheaf. So that means that the underlying sheaves, the Frobenius pullbacks of the E should actually glue. And they glue to something that I called F here. And now, what happened to the connections? Well, if you work this through, and this is just working out what the equations that I've already written down imply, what you end up with is a sheaf F on X, one sheaf, like it's not just a bunch of sheaves satisfying some cocycle conditions, it's an actual sheaf F, but it's only equipped with locally defined connections, nabla I, and they don't agree on the overlaps, instead they satisfy this equation that I wrote there. And so that's, I mean, that's one consequence of that is that you get an equivalence of categories that looks sort of like the one that I wanted. The equivalence is between coherent sheaves on X and now it's coherent sheaves on X, not equipped with a connection, but equipped with a bunch of local connections that satisfy some sort of compatibility on the overlaps. And the compatibility is phrased in terms of these betas, and the betas ultimately depend on alpha. So it's some kind of condition on alpha. Okay. So I mean, this is sort of like just applying Cartier descent directly and looking at cocycles. This is what you get. There's one condition, or let me say something about this cocycle d beta ij over beta ij that showed up. This is a class in H1 of omega 1, and you can describe this class kind of directly in terms of alpha as follows. There's a short exact sequence like this, multiplication by p on GM. And notice here this multiplication by p is injective on GM if we're in characteristic p and X is reduced. So when you're multiplying by another number, you'd have some kernel like mu n, but here, this is at least as a sequence of Vitala sheaves, multiplication by p is injective. And there's a boundary map, which goes from H1 of GM mod GM to the P to the Brouwer group. And this choice of cocycles beta ij is the same thing as choosing a lift of alpha onto this boundary map. And the induced class in H1 of omega 1 is just given by taking d log of this. Where here by d log, I mean the map that sends f to df over f. Okay, so in any case, there's some sort of cohomology class at H1 of x omega 1 that intervenes and that is defined somehow in terms of alpha. Okay, so let me describe now kind of there's a more canonical way of viewing this this equivalence that that I worked out that I want to describe now. So this is sort of the cocyclic description. And I want to describe kind of a more sort of like a more abstract but more direct way of getting at this that doesn't involve cocycles at all. So there's sort of a general, I mean, here's like a little gadget or something that I'm going to define, and then I'll say why it's relevant in a second. So a restricted Picard algebroid, that's just my word for it. It's a short exact sequence like this of restricted Lie algebras. So here, the tangent bundle of X is a sheaf of Lie algebras. It's equipped with the usual bracket. It also has the structure of what's called a restricted Lie algebra, which also incorporates this p iterate operation. So this is what I'm going to call a restricted Picard algebroid. It's a short exact sequence like this, and there's some axioms that I didn't write down that this map alpha has to satisfy. So this is at least the Picard algebroids are. If you forget the sort of restricted structure everywhere, this is something it's called a Picard algebroid that I think is sort of a kind of a fundamental construction in suitable some area. So this is kind of like a characteristic P version where I'm also incorporating a restricted structure. Okay, so I'll say how these gadgets arise in this setting in a second. But one thing you can do to these things is classify them in terms of cohomology groups. So this is something you can show. You can show that these isomorphism classes of restricted Picard algebroids are classified by this particular cohomology group. So specifically, this is I'm taking the cohomology H1 of this two-term complex, Z omega 1 to omega 1. The map being the Cartier operator -1, and yeah. So this is it's some kind of little sort of. There's a bunch of these on a variety X, and you can classify them in terms of some cohomology group, isomorphism classes. But just to to orient you, if you take a restricted Picard algebroid, in particular, it's an extension of OX modules. It's an extension of TX by O. So it has a class in H1 of omega 1 also. And these two things are compatible. There's a map from the two-term complex Z omega 1 to omega 1 to the sheaf omega 1 given by the inclusion Z omega 1 to omega 1. So it's 0 and it's injective in degree 0 or 1 and 0 in the other. Right? So this comment was just to orient you. It's this is how you get the underlying extension of OX modulus. Okay. Now I want to describe how these restrictive Picard algebroids arise in my setting, because they arise in kind of an interesting way. So I'm going to return to the setting where I have a p-torsion class in the Brouwer group, and actually associated to such a thing is a restrictive Picard algebroid in some kind of canonical way. So here's how the association goes. Take a class mapping to this class in the Brouwer group, lift it to H2 of X mu P, and consider a mu P gerb corresponding to this class. So that this is an algebraic stack over X, which is what's called a mu P gerb, and I guess this is sort of a geometric way of looking at second degree cohomology classes. The isomorphism classes of mu P gerbs over X are in bijection with H2 of X mu P. Okay, and now here's one thing you can show, because we're in characteristic P and the Frobenius sort of acts as multiplication by P. Basically, if you pull back your mu P gerb by the Frobenius, it becomes trivial. This is basically, if you pull back the cohomology class in H2 of X mu P by the Frobenius, it becomes 0. So one way of writing that down in terms of a diagram is what I wrote here, that there's a map from X to the gerb. It's not a section of the map from curly X to X, but it's a sort of a section after you pulled back by the Frobenius. Okay, and this might be kind of reminiscent of what's called a foliation. A foliation would be where you took this, instead of curly X here, you just had a scheme like Y. That would be what's called a foliation. So this is some kind of like stacky foliation. And now from this diagram, you can produce a restrictive Picard algebroid as follows. You can take this distinguished triangle of tangent complexes associated to this map to this commutative diagram. And now if you just basically look at this sequence of tangent complexes, and you take, I guess, H0 here, what falls out is a restrictive Picard algebroid. And so I guess I want to point out a few things here. One is the fact that you get an extension like this is really special to this situation. Like for instance, you could replace mu P by just some random group scheme G, like you could do like Z mod N or GM or something. And you still get some gerbs. And you can still look at various sequences. I guess there wouldn't be this map Fx and pi in general, but you can still look at various distinguished triangles and tangent complexes and stuff arising. But you're never going to get an extension like this. And the reason, the thing that's special here basically is that this group scheme mu P is non-smooth, which means that its derived Lie algebra has cohomology in 2 different degrees. It's not, if it was a smooth group scheme, it would just have cohomology in 1 degree, but it's non-smooth, and that gives rise to extensions like this. And this shouldn't be surprising. Like, if there was some canonical way of associating an extension of OX modules to like a class in the Brouwer group or a class in like H2 of X Z mod N or something, I think it's like one of those, like, you probably would have heard of it sort of situations. So the fact that this exists is really special to this kind of mu P and characteristic P situation. Okay, anyway, so this is sort of like an amped up version of what I said before. There's actually an equivalence between mu P gerbs and restrictive Picard algebroids. They're kind of, you can get one from the other. And at the level of cohomology, this is reflected by an identification like this. So H2 X mu P is this cohomology group that I said classified restrictive Picard algebroids. Okay. what's the relevance to Cartier descent? I claim this was like my sort of more canonical way of saying this Cocycle result I said before. Well, from a restricted Picard algebroid, you can make some kind of restricted universal enveloping algebra construction, which takes into account, so a restricted Picard algebroid is in particular a restricted Lie algebra, and you could take the universal enveloping algebra of that. This is a variant of that where you also are incorporating sort of this map alpha and this map from OX to L. So there's some construction you can do to this, and this is really, I think, the canonical way of saying what's going on is that coherent sheaves for alpha twisted coherent sheaves are the category of such things is equivalent to the category of modules for this restricted universal enveloping algebra. So this, yeah. So in particular, for instance, if you were to apply this to like, I wouldn't say it's a special case, but if you take like the, you could also take the restricted universal enveloping algebra of say of the tangent bundle, and in that case, there's a similar way of stating like a module with an integrable connection in P curvature 0 is the same thing as a module for a certain universal enveloping algebra. Okay. In any case, this is sort of the twisted version of Cartier descent, and I think this is also I'll point out this is again, this is very special to this setting. In general, if you have alpha twisted sheaves, say in characteristic 0 or when the Brauer class is not P torsion, there's no way of expressing those as like modules with connection or modules sort of untwisted sheaves with some extra data, at least in any canonical way. So this is like,
yes, but in some sense, this is the same as in as was earlier, because module with integrable connection is a D module, and here you really, I mean, D is simply the universal enveloping algebra of this tangent Lie algebra, right?
Yeah, absolutely. Yeah. I mean, this is a this is essentially Cartier descent for sort of groupoid schemes is essentially what's going on here. But sort of, maybe you could make it a little more kind of like detailed in the case of UP gerbs. Is how I think about it. Okay, so why is this relevant? My point or my goal was to compactify these twistor spaces, and what I've done is sort of made an equivalence between alpha twisted sheaves and some other thing. Oh, actually, before I say that, here's a special case of what I just said that I think is like particularly where you can make it particularly concrete. And I think this is actually kind of cool. So let me just say a few words about cohomology before I write down the more concrete formulation. So I'm going to start with the supersingular K3X, and here's a bunch of relevant cohomology groups. I have H2 of mu P, H1 of Z omega 1, and the full de Rham cohomology. I haven't told you actually what this embedding of H2X mu P and H2 dr is, but there is a canonical way of doing this. And by what I said earlier, the kinetic component of H2X mu P is a copy of A1, and so there's some kind of subgroup of H2 dr which is isomorphic to A1. There's another subgroup which is given by a piece of the Hodge filtration. You could also looked at F2 of the Hodge filtration, which is equal to H0 of X omega 2, which is isomorphic to K. This is a line inside of H2 dr. And every once in a while, these two subgroups are equal. So it's specifically, I said if sigma naught equals 1, sigma naught is some invariant attached to a supersingular K3 surface. For some supersingular K3 surfaces, sigma naught is equal to 1, and that turns out to be equivalent to these two subgroups being equal. So why I'm bringing this up is because in this situation, giving a class in the connected component of H2 of X mu P is the same thing as giving a class in F2 of H. In other words, a symplectic form on a supersingular K3 surface. So now my question is, can I rephrase what I said before in terms of this symplectic form? So if I pick an alpha in the connected component of H2 of X mu P, that's the same thing as picking a symplectic form on my K3 surface. And here's something you can work out. That the equivalence that I wrote down on the previous slide, in terms of this restricted universal enveloping algebra, you can phrase modules, you can write down concretely modules over such a thing in the following way. It's giving a module for that thing is the same thing as giving a coherent sheaf on X with a connection satisfying these conditions. First of all, the curvature, which is an element of, it's a global section of end E tensor omega squared, is basically equal to this symplectic form. And then there's also a condition on the P curvature. So in this case, you don't have to actually mention this restricted universal enveloping algebra. You can rephrase what it means to have a module over it just in terms of the symplectic form. So I found this kind of cool. Because this is, I don't know, this is at least like feels a little more hands-on to me. Okay. So this is one special case of the previous construction, in which case, in which you don't have to mention some of these, you don't have to mention kind of all the general constructions. Okay, so why is this interesting? I said I wanted to compactify my supersingular twistor spaces. So what does this buy you? The fact that I've rephrased alpha twisted sheaves in terms of some other, I have some kind of formal equivalence of categories. Well, there's one more operation that you can do when you sort of put things in that setting. So the extra operation, or the extra sort of thing that you have is that a restricted, these universal enveloping algebras, they're filtered, there's sheaves of associative filtered algebras. They have a filtration of them. And that lets you do things like basically what's called the Reese construction. This basically, it lets you deform to the associated gradient. So let me tell you what the output of this stuff is. So I said I had this curve U, which is inside of the Durand cohomology. So I'm going to take its projective closure. This gives you some rational curve, and one you can write down really explicit equations for this curve, but it ends up either being P1 if the Artin invariant is 1, or it's some kind of cuspidal curve in general. And its normalization is P1. So I'm just sort of setting up notation here. So I'm going to let P1 sub TW, that's like the twister P1. I found it helpful to put a subscript on it. I'm going to define that to be the normalization of this curve. And by the way I've constructed it, it has, it's basically, I took this U and I added 1 point at infinity. Okay, but here's the output of applying kind of a Reese construction in a suitable way. So I've already told you how for each point away from infinity, you can get a restricted universal enveloping algebra, which is some kind of sheaf of filtered algebras. You can actually extend that sheaf of algebras to a sheaf of a flat sheaf over X cross P1, which I call D sub TW. And it has the following properties. If you look at a fiber over some point away from infinity, then modules over that sheaf of algebras are equivalent to just giving alpha twisted sheaves, where alpha is the class corresponding to that point in the A1 or in the U. But the key thing here is that I've added a fiber over infinity, and that's where kind of the really interesting stuff is going on. And here's like at least here's one thing you can show. A module for such a thing is in particular a Higgs sheaf on X. So in other words, what I'm saying is that in particular, what I'm saying is that the fiber over infinity of this D is a commutative algebra. So another word that applies to situations like this is basically that this DTW is it's a deformation quantization of the fiber over infinity. The fiber over infinity is a commutative filtered algebra, And all the other fibers are non-commutative, but they deform that fiber. Okay, so this is kind of the benefit of leaving alpha twisted sheaves and rephrasing them in terms of modules over a filtered algebra, is that you can compactify that sheaf of algebras. You could not compactify the Bragg class. There was not a Bragg class over P1 that extended, but you can compactify the sheaf of algebras. And it follows from results of I said Simpson here, and I think definitely some other people, that you can take moduli spaces of semi-stable modules over such algebras. Okay, so that's kind of this is kind of like the starting point for my investigations. Is I now have this gives you a candidate for some construction that should compactify the families. You could take a moduli space of, now instead of alpha twisted sheaves for this universal alpha, you could take a relative moduli space of D modules on X cross P1 over P1. Okay, so here's what. And let me. I can actually, in this case, in the art invariance 1, you can also unpack this thing, unpack this very concretely, and say what modules are over this whole P1. So here's what this. I think this is kind of fun. So if a T connection on a coherent sheaf it's kind of like a connection, but it satisfies this modified Leibniz rule where I stuck a T in the right place. And T connections scale. So if you have a T connection and you multiply it by some scalar, you get a mu T connection. Okay, and by what I said earlier, this twister P1, there's the projective closure of this U inside of the de Rham cohomology. And then I also said that U is equal to the second piece of the Hodge filtration. So the twister P1 in this case is it's basically the projective closure of the second piece of the Hodge filtration. And here's the output. You can kind of unravel all this stuff, and you get that. Give me a coherent sheaf for this twister algebra D over a point in this P1 now is the same thing as giving what I wrote on the right hand side. So a coherent sheaf with a T connection whose curvature satisfies its curvature is equal to T tensor the symplectic form, and also then there's a P curvature condition. So I think from this description, you can kind of see what's going on when you let, if you let sort of T go to infinity, and if you let sigma go to infinity, but like keep T being equal to 1, that's kind of the same thing as like, that's letting sigma go to 1, but T go to 0. Okay. Okay, so that was, I find it kind of pleasant that you can unpack this in such a concrete way in at least this special case. Okay, so let me now kind of summarize what I said earlier about this being a mechanism to compactify the twister spaces. We can now do the following thing. So let's start with the supersingular K3 surface. Take a primitive Mukai vector. Let's say we pick the Mukai vector and our polarization suitably so that this twister space that I defined earlier is nice. Like, okay, I said smooth symplectic varieties here. You could even ask for them to be K3 surfaces, or you could also look at higher dimensional ones. Okay. Here's my mechanism to compactify, or my candidate. I'm going to define W to be this. W is this is the Mukai vector of the pullback of a sheaf with Mukai vector V. This is just, you can just compute what W is, and it's this. And you can look at the relative moduli space of D modules on X cross P1 over P1 with Mukai vector W. So by kind of general theory, this is a proper, a family of proper varieties over P1. So that's nice. And if you look away from infinity, it recovers what I had before. by this equivalence between alpha twisted sheaves and D modules. Okay, but what's going on at the fiber at infinity? Well, the fiber at infinity actually, at least as I've stated here, will be much larger. It'll in particular usually have much larger dimension. And this is one thing you can work out if you like square this W to see what the expected dimension of the moduli space is. I mean, like the fiber at infinity, I said it was certain Higgs sheaves. So like an example of a Higgs bundle is you just take the trivial, you take the Higgs field to be 0. So in particular, a coherent sheaf on X with a 5 vector W gives you a point in the fiber at infinity. And so you can work out what the expected dimension of that locus is by squaring W, and it's going to be much larger than the dimension of the other fibers, almost always. So, okay, this family that I wrote down, this M, is definitely not flat because the dimension at infinity is jumped. Okay, so that's bad. But I mean, what's like the minimal thing you could do that you would hope would correct this is you could take the closure of all the other fibers in the whole thing. That'll give you something that at least has the right dimension. Every fiber has the right dimension. And it'll also be flat. And you could also normalize it. I mean, you know, maybe just in case, maybe it's not normal, you could normalize it. Okay, so this is like you could attempt to do this and hope that the result is nice. So that's what I'm going to call math frac V. It's what you get if you take this M, you take the closure of the other fibers in there, and then you normalize. My question is, when is this smooth? Is it, yeah, I mean, more generally, what can you say about this? Like, you could hope it's smooth. It's at the very least it's a flat family of proper varieties over P1. And all the fibers away from infinity are smooth. And the hope is that the fiber at infinity is also smooth. Like I said, from general theory, we know that there is a way of compactifying it so that the fiber at infinity is smooth. Maybe this is it. Okay, so what I want to finish on is say one case in which I have, I think, a pretty thorough understanding of what's going on with this family. This is what I call the rank 0 case. So you take a curve on X, I call it C, a smooth curve of genus squared than equal to 1, with primitive Picard class, and consider the universal curve. Here's my condition on that guarantees this smoothness. If the Kodaira-Spencer map of the universal curve is generically injected, then this family is actually a family which is actually smooth. The fiber at infinity is smooth. And I can also say, I mean, and you can. The proof of this is you can really understand what appears at infinity very concretely in this case. And I should say when the family is not generically injective, you can also say very specifically what happens. In that case, the fiber at infinity is, this normalization really is non-trivial. And actually what happens is that the fiber at infinity is basically kind of it's a Frobenius descent of the fiber over 0. So you can say very specifically what it is, but that's what happens. Okay, I'll stop there. Thanks.
All right, let's thank Danny for the beautiful talk. Any questions?
Or maybe comments?
Yeah.
If I can, actually, I didn't quite understand why you worried so much about this sigma 0 equal to 1 case. The point is that in your case, you really care about modules over this restricted, say, sheaf of differential operators over this Lie algebroid, but the modules over these are exactly equivalent to modules over this Lie algebroid with 0 p curvature, and you can actually reformulate them in terms of connection, but now the connection wouldn't have values in the cotangent bundle, but in the dual of your of your L, right? And then it would be integrable connection and so on. But I mean, the description is completely clear in this case, right?
Yeah. The point is merely that when sigma naught equals 1, this extension of the algebroids is split as a sequence of OX modules. So you can rephrase things in terms of like T connections if you want.
Yeah, but here you also have lambda T connections and so on. I mean, there's no problem with that.
Yeah. It's not it's just a formal sort of reformulation of the definitions. Yeah. I think the reason why the thing that I find particularly interesting about it is the fact that that giving in that case, giving a class that you can rephrase things in terms of the symplectic form, which I think is actually kind of, I mean, the fact that like giving these sort of like Brouwer classes on X are actually the same thing as symplectic forms on X is kind of, I find it kind of striking. I mean, I don't know if it's, you know, I think that was the reason why I wanted to sort of highlight it.
Any other questions, comments, remarks? All right, let's thank Dan again.
Thanks.
Actually, yeah, now I can make another comment.